Next speaker is Amat Hussain, who is coming from us from Solarflare Communications. He has a very strong background in storage, having worked at QLogic, developing 25 gigabit per second internet, and has worked at Intel and Honeywell. And you may recognize him because he's been a prior speaker here. He has the distinction of having won the Intel Achievement Award and being a founding board member of the Storage Networking Industry Association, and has presented keynotes at past flash memory summits, so you might recognize him here. But, you know, he's also got a personal life aside from this. Ahmed is a very, very rabid soccer fan. Having been raised in England, he always cheers for the English team, which I think that probably preoccupied him for an awful lot of the past couple of weeks as the World Cup was playing out. Anyway, I'd like to invite Ahmed up to the stage to give us his presentation.
Okay, lunch must be better than my speech, so everybody's going. So let me tell you a little bit about Solarflare before we get going. Solarflare is a networking company based on Ethernet, and what we do is low latency. And we've been doing this for about 10 years. So we run on standard networks. Our solutions drive the lowest latency. In fact, in the last few months, we've been announcing latencies in the 150 nanosecond, 120 nanoseconds across Ethernet. And if you want to find out about that, come and talk to me afterwards. But today, what we're going to talk about is really the data center, where it has been, where it's going. Last year, I presented this picture where I said storage area networks, SANs, and network-attached storage had been predominantly built on very, very high-performance, dedicated proprietary environments. With the advent of flash and with the advent of where the data center is moving forward, the data centers don't look well organized like this anymore. They look like this. Large, sprawling networks, lots and lots of servers, lots and lots of different ways of connecting and communicating and virtualizing. The need for high performance, low latency transactions across that network's become critical. And this is a well-established network. So if you want to go into a modern class cloud or cloud style, we call them cloudy networks, this is what you're going to find. Not a well-organized infrastructure. So how do we make flash available in those environments? And that's what my talk is going to be about today. So if we look at the evolution of flash, you know, in the early days, it's staggering to think about it this way. If you think about a fastest HDD drive, hard disk drive, back several years ago, not many years ago, was in the range of maybe 7 millisecond access latency time. 7 millisecond. Today, if you just roll the clock forward today with what Rob talked about, Optane, 10 microsecond. The factor of improvement on the drives itself is really driving a new momentum around what we do with this storage from a network perspective. So if you look at it from that perspective, you have SSDs. And one of the first problems SSDs faced inside a server was the architecture, the way it was designed for 7 milliseconds. So with the advent of NVMe, the new style of connectivity, we eliminated that bottleneck. So the first step was make SSDs really viable inside the network. That was what's established several years ago. And there's been several people took that technology and said, how do we put that across the fabrics? So there's been some early adoptions around fiber channel, InfiniBand, and Rocky-based Ethernet. We think that's a problem right now because it's limiting the adoption. When you go back to the previous picture where I showed you, the sprawling network, it's all based on TCP/IP. It's not tolerable of new classes of protocols to go on top of that. So the adoption has a big barrier. Our mission was, can we take what we know and the industry and create a solution for the industry that would allow it to run on native TCP/IP? That's what we've been doing for 2 years. And it's almost 2 years since we started this project of figuring out how to take standard NVMe over fabrics and put it on top of native TCP/IP without additional protocols. And we've actually come to a point where we can now demonstrate this. We have product, and the spec, I believe, will get ratified very shortly in the next couple of months. When the TCP spec gets ratified, here is the results you'll see. In this particular graph, we show the latency of a local drive. That's the white line running across. And underneath that, you'll see the equivalent, but this time it's running remotely across TCP, across a fabric to that solid-state disk. And you can see that it's within hair's breadth of local, right? This is another view from a latency perspective. You can see there is around 10 to 15 microseconds of latency that we add because of this network stack, but all of it is pretty much driven around the latency of the SSD. So TCP, from a latency perspective, on top of, NVMe OF on top of TCP, from a latency perspective, is within a hair's breadth. And this is a lot of the technology that we drove. And what we also wanted to do here is make this TCP plug and play. It means that if you take the NVMe plugin, TCP plugin, you drop it into your system, it will work with any stack, any TCP stack underneath it, because it sits on top of POSIX-compliant sockets. So there's no barrier between it and being deployed everywhere. Here's another view from a bandwidth perspective on top of each other. So if we just take a moment here, what we've demonstrated is very fast, 100 microsecond range SSDs being connected across the network with barely any performance impact associated with that networking. And it's on standard TCP/IP. As the bandwidth of TCP/IP goes from 10 to 25 to 100, and we're actually working on a project that's into terabytes per second networking, this technology will flow automatically without you having to rip your networks up, reinstate networks to do that performance. So the value of what we would like to enable in the industry with our partners across the board is this type of solution. So if you look at it from this analogy I have here of a toll booth, the SSDs with NVMe Express, we've cleared it out, made it a fast lane, so you can take your SSDs with NVMe Express solution and put it inside your server and get the benefits and the performance. We believe that's done, has been for several years. We've now at a point when we're saying NVMe over TCP is a proven technology as well. And what the numbers I've showed you was not our numbers, was done by third-party partners who tested those environments themselves. But we think there's another barrier coming. And I'm going to talk to you about some of the drivers. Rob talked about these drivers in the industry. That's going to create another bottleneck, and that's within the system itself. And then how do you make networking work within those barriers? And we're going to get to that a little bit later on. So we think this next barrier is all around the bottleneck associated with systems and servers and the operating system. How do we continue to improve the latency and the performance and throughput as you reduce the latency of the devices and as you increase the performance of the networks? So that's the next barrier, and I'm going to get to that. But before I get there, I want to sort of repeat what's been said already. One of the amazing things I look at in the industry when you look at it as a whole, these connected devices. Now, everybody says, what's connected devices to do with storage? Very simple. These connected devices generate data. Data's got to go somewhere, it's going to be used and done. When this data comes at you with nearly 30 billion sensors enabled on a network, that's a huge amount of data that you're generating. Flash devices, storages, will be able to hold that from a capacity perspective and performance, but they're useless if they sit in isolated buckets and you can't have applications connect to them. So there's an underlying theme here about what do you do when you fill the environment up with this data and how do you use it. Another thing that I think is going to be a game changer. Within the next year or so, you'll start to see 5G networks appear. I don't know if people recognize this. What 5G is Wi-Fi, speeds. And one of the things 5G addresses is latency. So your devices now can generate data at latency rates that are unheard of. So if you think about edge computing, you think about flash storage, how does that all get together and work effectively? So this explosion of data driving the need for analyzing the data is creating new demand. So as soon as the Optane device class comes into being and people start using it, they're going to say, how do I connect it? How do I access it? So we think there is a barrier and a problem here that needs to be addressed. So the other thing that I also wanted to touch on is very often people look at data centers and they think about CPUs, but they don't realize what's happened since Moore's law slowed down. The number of cores in a single CPU is growing. What's the implication of cores to do with storage and networking? Well, cores run many, many applications concurrently. So you take a 72 core and multiply by 100 servers, you've got 7,200 interconnected cores, and if you multiply that by 4 threads, there's thousands of instances that would want to access data. So allowing those servers and those instances to access data at the lowest latency level from a device to the network is a critical aspect of improving efficiency for those huge analytic applications and AI stuff that's coming down the pipe. So if we then take that and look at this sort of an environment where you have all these different types of solid-state disks inside servers, dedicated storage, application servers, the thing about this is that with the Optane introduction of the Optane class solutions, you're down to about 10 microseconds on latency on devices. So how do you create a microsecond access to that data? And what are the key barriers that's preventing us from going forward? So if we look at that, we think there are 3 distinct areas that these barriers will exist in. One is clearly in the networking. The other one is in the operating systems. Operating systems were designed to be very monolithic. That means if you have a device connected inside the operating system, it tends to be accessed through the operating system. And in a lot of the low latency stuff that we've worked on in networking, the operating system bottleneck is always a crucial factor associated with latency. So now let's dig in underneath this and look in what are the main causes for these things and what's the easiest way to address them. So if you look at inside the server today and look inside the server in terms of bottleneck, one of the key things you'll find out if you have a bunch of disks, inside the kernel space, you'll have an API, some block and file layer, some NVMe and drivers, and you connect up to the speed. So every time a virtualized app wants to connect to that SSD and do some action, I mean, SSDs have up to 64,000 queues. You can put a lot of things there. It's got to do a context switch. That context switch is a heavy penalty inside these very high performance devices and high performance, high core count environments. It creates a bottleneck. So ability to scale a single server with this sort of model becomes very, very difficult. All you can do is add more CPU power and improve the efficiency of the code running in the kernel. But there's an alternative that we at Solarflare has driven from the network called user space networking, and there's user space block device enabled by SDPK. So this is something that between us and Intel, we did recent analysis on Optane, and we'll cover that data in a minute. But putting the application's ability to communicate directly with the SSD without touching kernel space and overcoming that bottleneck that exists inside the operating system is a key factor of removing one of the performance bottlenecks in the system. So user space is a very efficient and effective way of avoiding the overhead. And in fact, if you look at this architecture, it's leaning towards, if you guys have been looking at the future of what's happening with operating systems, microkernel architectures start to really come into play. But this is beforehand, we can use this in SDPK. So with SDPK, we can eliminate this overhead of copies, buffers, switching, and everything else within the server. Well, what happens if you take this and you add to it networking? If I did your typical networking, I don't show it on this picture, but let's say you put network interface controller, You put it into the kernel, there's a driver, there is a kernel mode application, whether it's Rocky or TCP, it's still going through the kernel. With our solution on user space TCP/IP, fully compliant TCP/IP, not only can we allow applications to bypass the SSD overhead associated with user space to kernel space and back, we can also allow data to move directly from networking into the application. So if you've got an application on the left-hand side that wants to talk to an SSD, it doesn't have to go very far to get that. It gets it directly. So therefore, we eliminate this performance bottleneck associated with networking. And this is the way we reduce latency in TCP/IP from our previous past. This is the technology we've been using. Not only our adapters are capable of supporting thousands of instances talking directly from user space to it, but we eliminate that overhead. So proof is in the eating. So this is some of the tests that we've done recently. And just to give you an idea of how to read this chart, on the left-hand side is microseconds. And if you look at the obtained latencies around 10 microseconds, so if we put the regular Linux-based kernel NVMe over TCP and ran it against an Optane device, you'll see that the latency around 37, 38 microseconds for 512 bytes and about nearly 40 microseconds for a 4K block. If we put SPDK, you got a reduction of 35% in the latency. And if you add our onload technology, which is user space TCP/IP, you get it down to about 44% to 44 to 54% of the overall latency is eliminated. So this now allows us to scale at the same rate across the board. I just want to stand back and make sure that we understand this. So what we are proposing here is that we remove the bottleneck of the operating system, but we maintain consistency. SDPK does that, onload does that with your operating environment, whether you're running containers, whether you're running virtualized environment, it maintains consistency. It allows you to access from any point on the network that storage with the lowest level of latency. So as you scale your wire speed on Ethernet, as you scale your SSD performance, there is no bottleneck in the way of that. It's all about data movement, straight out the application, straight to the SSDs and back. So this is what we're proposing in this solution set today. And so if you look at the result, this is the first blush of these results. We also looked at it in terms of IOs per second, the same effect. Bandwidth, the same effect. So you increase IOs per second, you increase bandwidth, and you reduce latency. And for me, when you look at these class of SSDs into the future and further reduction speeds, and when you put them inside all-flash arrays and you reduce the latency further from that perspective, now things start to really look interesting. We think this is the next stage in the evolution of NVMe over Fabric and TCPs. Okay. So let's step back for a moment. The key thing to success for NVMe over Fabrics is allowing everybody in the industry to gain access to it without having to pay the penalty of upgrading your network. Let's say, for example, you go into a customer that has 100 installed servers, or maybe 1,000 installed servers. I want to roll in a new all-flash JBOF or an all-flash array into your environment running on NVMe. The first thing you're going to say is, by the way, this NVMe over TCP and the way it's implemented will force you to change your network to make it work more efficiently. That's a very difficult uplift for many customers. Some customers will take it because they need the performance. Some customers won't. But moving into a standard TCP/IP infrastructure and not forcing that infrastructure to be changed and modified will simplify the adoption of NVMe over Fabrics. And then eliminating the barriers associated with the performance inside the servers for networking and access to the NVMe devices, that will also further enable that and reduce that barrier of entry. So our vision is over time, we can move the technology across the board for many instances. and not force customers to go through full upgrades to implement that solution set. Okay. I'm running fast today. Sorry. Okay. So, you know, we at Solarflare have been looking at latencies across networks for quite a while. And one of the things that we've identified, there are certain key elements associated with latency and networking. And one of those is we tend to think about it is in terms of the adapter itself, the network interface adapter. That's only part of the problem, and it's actually a small part. A lot of the latency in networking is introduced by the software itself. So there's a tendency out there to move software out of operating systems and your server into the hardware device itself. That's certainly a way to improve latency, but there's only a certain level of efficiency. Now you're down to the wire speed and the latency. So if you look at a typical adapter from us and compare it to other adapters, we run on average from the memory to the wire around 300 to 500 nanoseconds. There's not a lot of data speed to cut out there. It's all to do with what you do in the software, how you organize your data structures, how you organize your applications, and especially in the highly virtualized environments, how efficiently you move it out of the application space to the wire. We've been working on a lot of technologies to address that. In fact, just recently we announced with LDA Technologies doing data movement from an FPGA accelerated solution. We drove it down to almost 120 nanoseconds. From the point we say send the packet to the point it hits the wire. So this is not the barrier. The big issue that we really have to address is ubiquity and making it easy for people to deploy this class of technology. And standing around TCP/IP and networking is the right place. So I'm going to give you a little bit of a vision of the future and maybe a little teaser for next time so they can invite me back up here to talk to you about the next thing that we think is happening. Smart NICs are starting to really become a critical aspect of the networking in the modern style. Smart NICs tend to have a lot more efficiency and capabilities to offloading types of actions like encryption and decryption and certain other things into a device that could be software programmable and as well as being software definable. One of the visions that we have for SSDs or flash memory and networking is to utilize this smart NIC to create you a unified JBOF solution that does not include an operating system and a server infrastructure to implement it. So giving you the raw performance of the SSD directly to the Ethernet pipe that exists in your infrastructure. So this is something that we'll talk about more, hopefully next time I'm up here. So with that, it's going to leave me about 5 minutes for open you and then allowing you to go lunch. So I'm going to open it up for Q&A. And anybody have? Yes, sir.
Excellent presentation, very clear. I'm KRS Murthy. Can you address any applications that you have tried or trying in high performance computing? And where speed and the amount of data are both at the same time, not just the speed, not just the amount of data that you do, latency and veracity of the data.
Yes, so we have run it. In fact, in our booth, we do have a MySQL database engine running, showing you that running across local device and running across remote device, you get the same performance, same responsiveness, and same data capability. So we have done that. Okay, with that, thank you very much. I think everybody's going to lunch. Finished early.